Okay, section 3.2, using second derivatives to find maximum and minimum values, and then sketching graphs. So this is going to be very similar to section 3.1. We're going to be talking about the second derivative test. Derivative test. And secondly, we'll be graphing some functions. So just like in 3.1, the second derivative test and second derivatives gives us an alternative way to look at properties of our function to be able to make a calculus quality graph. So we can do decent graphs just like we did in 3.1 using what's called concavity and looking at intervals of concavity. So defining concavity here, we need a differentiable function. And remember that this also implies that the function is continuous on some open interval. Then we say the graph of f is 1 concave up or I'm going to use CCU as a little shorthand. And this is if f double prime of x is greater than 0 on that open interval a to b. And so we're concave up if the second derivative is positive. And that means, you probably guessed, we are concave down CCD if f double prime of x is less than 0 on that same interval, a to b. Right, so we can't be both. We're one or the other here. So we're either concave up or concave down. Now I have a little diagram here. I know it's a little blurry on the camera, but hopefully you're looking at this either on your screen or on your own paper. But you can see we have a straight line here. This has no concavity. When we're concave up, it curves up slightly, and when we're concave down, it curves down slightly. Now the amount of concavity can be different. We are basically going to be classifying as either concave up or concave down, not necessarily how steep the concavity is. Because you can have something very steep like this is still concave up, and something very slight like this is still concave up. And we're not going to distinguish between the two. We're just going to identify when it's up versus when it's down. So we have a test for concavity. So if we let f be a function whose second derivative exists, because we got to be able to look at its second derivative on an open interval a to b, then we choose a c. X equals c in that interval a to b. And if f double prime of c is greater than 0, then we can say that f of x is concave up. And if f double prime of c is less than 0, we can say that f of x is concave down. So this limits what we need to check. We don't need to check all of the values, we just check one. And the reason for that is if it switches, when we switch concavity from up to down or down to up, we have what's called a point of inflection. So a point of inflection is defined this way. So if x equals c is a point of inflection, which I'm going to call POI, then f double prime of c equals 0 or is undefined. So the way that we build our intervals up here in our test for concavity is our A and our B become these points of inflection, so that we can guarantee it's only one or the other in between, which is what allows us to do this. So we're not going to test an interval that has a point of inflection in the middle of it. We would never do that. We would always find these points of inflection, build our intervals that way. Just like we found our critical numbers in section 3.1. And we built our intervals for increasing and decreasing that way. So again, I have a little diagram here. You can think of point of inflection as the switching point. It switches from concave up to concave down. The inflection point itself doesn't look like anything special. It's just in between those two things. And you can think of this as I say right here, a lot of my students typically say it's concave up if it can hold water, and it's concave down if it can't, if you were to imagine pouring water into it. But these points of inflection can be very obvious like this. They can also be very slight. So another example, something like this. This has a point of inflection because we do have a slight concave down here and a slight concave up here. So the point of inflection is somewhere like right in the middle. So keep that in mind. Your points of inflection aren't actually part of the concavity one way or the other. They're the only place where we have no concavity. All right, so let's talk about our second derivative test. And this is how we identify extrema. So we're going to let f be a differentiable function for all x in some open interval, and x equals c is a critical number. Remember, that means that f prime of c equals 0. So we still have to find those critical numbers. Then we have three options here. Number one, if f double prime of c is greater than 0, that means that f of c is a minimum. If f double prime of c is less than 0, that means that f of c is a maximum. And if f double prime of c equals 0, well then our test is inconclusive and we have to use the first derivative test. So you can kind of imagine what's happening here. So we find our first derivative, set it equal to 0, find the second derivative, and in number one, what we're describing is we have a concave up, something like this. And so remember, our first derivative being 0, that's where we have horizontal tangent lines. So if you think about this concave up feature, the only place we can have a horizontal tangent line is down here at the bottom. So that means that our critical number must be right here. And so that's what we're thinking in number one. And in number two, it's the same thing but opposite. So if we have this concave down feature, we're still finding horizontal tangents. And again, that can only come right here. So our horizontal tangent, pretend that was a horizontal line. But our critical number can only be right here, so it has to be a maximum. So a lot of students end up liking the second derivative test more because it's a simpler test. You're not testing values on either side like we did in the last section. But as you can see, there are going to be cases where the first derivative test is unavoidable. And the other thing to think about is the second derivative test requires you to find the second derivative. So you're not always going to want to take the second derivative. But when you do, or when it's okay and you think it's not too bad, I think the second derivative test is a very efficient way to test for extrema. So let's go ahead and try this out. So we're going to determine some weird formatting here. Determine the intervals in which the graph of the function f of x equals, this is 6 over x squared plus 3, is concave upward, and concave downward on the graph. And then graph the function. So I'm going to rewrite f of x. Since this is a constant here, I can bring our denominator to the top as 6x squared plus 3 to the negative 1. That makes f prime of x equal to negative 6 x squared plus 3 to the negative 2. That's using the chain rule here, or general power rule, bring the negative down, subtract 1, and then times the derivative of the inner, which is 2x. And so I'm just going to simplify a little bit here, negative 12x over x squared plus 3 squared. So what we need to do now to use our first derivative or our second derivative test is to find our critical numbers. So we need to set this equal to 0, our first derivative. So you'll notice in both sections 3.1 and 3.2, we take the first derivative, we set it equal to 0. You're always going to be finding your critical numbers because your maxes and your mins occur at those critical numbers. So whether you're using first derivative or second derivative tests, you have to find your criticals. So in this fraction, the only time that the fraction can equal 0 is when the numerator equals 0. So we have negative 12x equals 0, or x equals 0. So the next step is to find the second derivative. So at this point, we can use either version of this. We can use this version or this version. It doesn't matter which version of your derivative you use. I'm going to use this version, negative 12x times x squared plus 3 to the negative 2. So up until now, I've told you you need to make it a fraction if it's not a constant here, and use the chain or use the quotient rule. In this chapter, moving forward, you can rewrite all rationals as a product of a negative exponent here and use a product rule if you prefer. You don't need to, but you can. And I'll show that in this one. So if we use the product rule for the second derivative now, we have derivative of the first, negative 12, times the second, x squared plus 3 to the negative 2, plus the first, negative 12x, times the derivative of the second, negative 2, times x squared plus 3 to the negative 3 times 2x. So this is negative 12 over x squared plus 3 quantity squared. And this is going to be minus 24, 12 times, it's going to be minus minus plus, so plus. So this is positive 24 times 2 is positive 48. X times x gives us x squared, and this is over x squared plus 3 to the third. And then this is going to be negative 12 times x squared plus 3 plus 48x squared all over x squared plus 3 squared. So all I'm doing here is multiplying this term, this fraction, by an extra copy of x squared plus 3 to get my common denominator and be able to add it. And then we'll just simplify a little bit here, f double prime of x. And we have negative 12 lost my train of thought there. Negative 12x squared minus 36 plus 48x squared all over x squared plus 3 squared, or 36x squared minus 36 over x squared plus 3. This should be cubed, not squared. Cubed, cubed. So now we have our second derivative. We're going to want it simplified because, again, we're finding intervals of concavity. And so we need to set this equal to 0. Again, this is only going to happen when, excuse me, when our numerator equals 0. So this is when 36x squared minus 36 equals 0. And this is going to happen only at positive and negative 1, solving that equation for x. So these become our potential points of inflection. And what we need to do is test our domain outside of this. So we set up intervals very similar to what we did for our first derivative test at -1 and 1. And we need a pick. So I'm going to pick -2, I'm going to pick 0, and I'm going to pick positive 2. And so now when we plug these in, we're plugging these into the second derivative. So we're looking at f double prime of -2, we're looking at f double prime of 0, and we're looking at f double prime of positive 2. And we're doing this because we're trying to figure out what concavity each of these intervals has. So when you plug in -2 into this, well, -2 squared, this is always going to be squared, so it's always going to be positive plus a positive cubed, so the denominator, no matter what we plug in, will be positive. So we can kind of ignore that. So now we have 2 squared, or -2 squared, which is 4 times 36 minus 36, which is still positive. So that tells us that we are concave up, or concave up. If we plug in 0, denominator is always positive. Numerator now, 0 squared, turns this 0, makes it negative. So this becomes less than 0, concave down. And when we plug in 2, exactly the same thing happens as when we plugged in -2, because we're squaring the -2 and the 2. So this is definitely going to be positive, which means we're concave up, concave up. So with this test, what you'll notice is I picked our critical number at, or for one of our testing values. And oftentimes when we get to the graphing part, I don't think we're going to graph this particular function. We'll graph the next one. When we get to the graphing part, so we can go ahead and just eliminate that part. You'll see we'll want to know these intervals of concavity, and we're still going to want to test the critical numbers. So this is why I said the second derivative test becomes more useful a lot of times if you're willing to take the second derivative. Simply because you have to use the second derivative to find your intervals of concavity, and if you pick your numbers correctly, you can test your extrema for whether they're maxes or mins while you're testing for concavity. So you can kind of double dip here and get two pieces of information. So this tells us that x equals 0 is a relative max because it was concave down, so our critical value comes up here. It also tells us we are concave up from -infinity to -1, union 1 to infinity, and we are concave down from -1 to 1. So, if we turn the page here, just for future reference, when you have a discontinuous functions, you want to test or form your test intervals by using the points of discontinuity along with your points of inflection. So you're not just using your points of inflection, you want to build those intervals with your discontinuities in there as well. And make sure that you do that so that you don't miss anything. Because if you only use your points of inflection, there's a chance your discontinuities fall in that interval. So for example, on this last problem, if we had some sort of domain issue, something we couldn't plug in here, we would add that number down here to our split points, just like we did with -1 and 1, and we would test those intervals as well. So let's try this example here. Determine the intervals of concavity of the graph. This is x to the 4th plus x cubed minus 3x squared plus 1. So here we're just looking for intervals of concavity and points of inflection. So we have our first derivative, f prime of x, is 4x cubed plus 3x squared minus 6x. Our second derivative is 12x squared how strange. 12x squared plus 6x minus 6. We set this equal to 0. I'm going to divide by 6. So we have 2x squared plus x minus 1 equals 0. This happens to factor to 2x minus 1 and x plus 1. So we get x equals 1/2 and -1. To go back and take a look at your second derivative, no undefined points because it's a polynomial, back to the original function. No discontinuities because it's a polynomial. So our split points that we're going to set up here are just at 1/2, or actually -1 and 1/2. So we're picking values in between. I'm going to pick x equals -2 here, x equals 0, and x equals +1. So we're plugging that into the second derivative, -2. So when we plug -2, we can use our shortcut, our factored version. So we have -2, or +2 times -2 minus 1 times -2 plus 1. This is -5 times -1, which is going to be positive. So that means we are concave up. For 0, we're plugging in 0, we're going to have -1 times 1, which is less than 0. So that means we're concave f double prime is 0. We're concave down, like this. And for x equals 1, plugging in 1, we're going to have 2 minus 1 times 1 plus 1, and all of this is going to be positive, so this is concave up. So we're concave up. So our intervals of concavity, concave up from -infinity to -1, union 1/2 to infinity, or concave down from -1 to 1/2, and our points of inflection are x equals -1 and x equals 1/2. So remember, sometimes we can have points of inflection that aren't actually points of inflection. Just like we had in section 3.1, we had those critical numbers that turned out to not be maxes or mins. So there's going to be times where we're going to see concave up, concave up. So our points of inflection are strictly where they flip concave up to concave down to concave up. So when you're testing, remember I said our potential points of inflection are here, and so we are looking at where we have these values where it flips from up to down or down to up. And if it doesn't flip, if we went up, up, then we no longer call that a point of inflection because it doesn't inflect at all. It stays the same concavity. So this would be our final answer for this problem. So now we're going to graph using the second derivative. So we have our, this is x to the fourth minus 2x squared. So our first derivative, 4x cubed minus 4x. Our second derivative, 12x squared minus 4. So we're going to set this equal to 0. Dividing by 4, we have 3x squared minus 1 equals 0. Or x squared equals 1/3. So x equals plus or minus 1 over square root of 3. So these become our potential points of inflection. Double check your second derivative. There's no undefined points, it's a polynomial. Double check your function. There's no undefined points because it's a polynomial. So we can set up our splits at -1 over square root of 3, positive 1 over square root of 3. So one thing that we can do here, since our ultimate goal is to graph, before we pick what points to check, is to set our first derivative equal to 0 to get our critical numbers. So 4x cubed minus 4x equals 0. Divide by 4, x cubed minus x equals 0. X times x squared minus 1 equals 0. This gives us x equals 0 and x equals plus or minus 1. So if we do this first and we get these critical numbers, this gives us good points to test. Because since we're graphing, it'll be good to know where our maxes and mins are. So I want x equals -1, I want x equals 0, and I want x equals 1. And then we just test, excuse me, we test our second derivative here. F double prime of -1, f double prime of 0, and f double prime of 1. And again, we don't care what these numbers are, we're plugging them back into the second derivative. So when you plug -1 back into there, you're going to get 12 minus 4, that's 8, that's positive. So that means we're concave up. When we plug 0, we're going to get a negative, so we're concave down. And when we plug in 1, we're going to get 8 again, so we're going to be positive. So this is going to be concave up again. So this also tells us that x equals -1 and 1 are relative mins. X equals 0 is a relative max. And we can work from there. So if we plug in -1, well, let's do 0 first. It's easy. So we have f of 0. Plugging back in here is just going to be 0. So that gives us the point 0, 0 that we can plot. Then f of 1 is going to be 1 minus 2, which is -1. So we have the point 1, -1 that we can plot. And then f of -1 is also going to be 1 minus 2, which is -1. So we have -1, -1. And we can plot that point. So this gives us a good starting point, pun intended here. And all we have to do is match concavity. So we know we need to be concave up here, and concave down here. So if you have a pencil, you can do this. I'm using pen, so I need to switch to a pencil. But what I do is I just give myself that shape, that concave up, concave down. I realize you can't really see that on my graph. Make it a little darker. Like that. And this gives me an idea of how these need to connect. So I need to go like this to figure that out. So that means my graph is going to loop down, then loop up, and it's got to curve back. It can't go straight, and then curve down, and then back up, and then back down and up again. And this goes up something like this. And then, ooh, don't try and erase over pen, I guess. We just erase those points, plot these at 0, 0, 1, -1, -1, 1, and we have a fairly decent graph here of our function f of x. So there's a lot that we have to do to get here, and this isn't even a perfect calculus quality graph. Right now this would still be considered a sketch because it's missing some information. So let's flip the page. So I have a true practice for you here, and I want you to try this out. Now I will give you some hints. Your function is only going to have one point of inflection, so make sure you're checking that. And the graph of this is going to look, ignore those points, those bled through the paper. It's going to be at, what is it, it's 5/2, 1. And it's going to look something like this. So work through what we just did. Set up your intervals to test for concavity. Use the second derivative test on any maxes or mins, any critical values, and see if you can come up with a similar graph. Because again, this isn't a perfect graph yet. We're still building to that. All right, so the last thing to talk about in this section is inflection points in applications, essentially. And we don't have any problems here because I just want to discuss it. You're going to have some homework questions that ask you to do problems, word problems, but you can see here inflection, or yeah, this is infection, not to be confused with inflection, but it's based on temperature. And I know in the current climate of today, a little on the nose, but you know, I made this packet way before this. So our inflection point is the temperature ends its steepest rise and begins to moderate, right? So when the illness is first brought under control. So this is what we are as a society are trying to get to. We're trying to hit that inflection point. We talked about this when I showed you the data for the coronavirus was that last week? Yeah, it was last week. That's what we're trying to do. When you hear people say flatten the curve, they're trying to force this to happen later rather than sooner, because it flattens it out and it pushes that over here. It keeps the number of people sick lower. But that's the idea. That's the inflection point. And when you hit that inflection point, it means that the disease, the illness, whatever you're tracking, is starting to slow down. because concave up, we increase very fast. Concave down, we are decreasing, or we are only increasing at a moderate rate. Same thing here. This is a little less virusy. This is about money. So if you're investing, in this case, we're talking about an advertising campaign, the inflection point gives us diminishing returns. So at some point, you're going to be spending money on your advertising, and you hit this inflection point, and you're not going to get as much return on your investment. And that's the point where most investors want to stop investing, because here they're getting a lot of bang for their buck all the way up into this inflection point. And then when they hit this inflection point, maybe they were making $2 in sales for every $1 of ad money that they spent, and now they're only making $1 for every $1 spent. And eventually that's going to slow, and maybe up here they're making 50 cents for every dollar they spend. So they want to stop at about this point. Sometimes you go a little bit further just to keep interest up, like speculative interest. But most companies are going to want to stop when they hit that, because now it's no longer financially viable to keep spending money on advertising in this scenario. The big thing here is we want to make sure that we're distinguishing between slope and concavity. So slope measures steepness, so how fast it's increasing or decreasing, whereas concavity measures the curl of it. So concavity tells you basically, is the slope very drastic in the positive or negative direction or not. So I have the 4 versions of what we can have. So I know you can't read this too well. Let's see if I can push my camera lower so you can actually read it. Ooh. Almost lost the camera. So we have increasing, it's still not very readable, but we have increasing and concave up. So our first derivative is positive, our second derivative is positive, and the shape of the graph looks like this. If you have increasing and concave down, so our first derivative is positive, but the second derivative is negative, then our shape of the graph ends up looking like this. When we're decreasing in concave up, first derivative less than 0, second derivative positive, it looks like this. And when we are decreasing in concave down, first derivative negative, second derivative negative, it looks like this. So you can use this as a nice key for what your graph shape should look like. And it's why in the next section, in 3.3, we're going to be putting this all together. Because if we use these 4 building blocks, so to speak, we can get a very good calculus quality graph. Because now we know with the combinations of first and second derivatives what our function will look like, what the shape of the graph will look like. And so that'll be the next video lecture, and I'll see you then.